Evening, everybody. It's 5 o'clock, actually a minute after, on Tuesday. Time for some Calc 2. So today is going to be our last day of content for the semester. So we're going to finish going over differential equations today, separation of variables, some applications. Give you guys a little time to try some of the stuff you've been learning in the online lessons. So I'll put the worksheet in chat in case you don't already have it. A couple of reminders. So Thursday, talk about the final exam, answer any questions. So it's an open day. Next week, we don't have any class meetings. Tuesday, I'll be proctoring an exam on campus during our class time. Thursday, I'll be proctoring the exam via Zoom during our class time. You can go to either of those, whichever you like. You also do have the option of using ProctorU if you'd like to choose another day and time. Just schedule using the instructions in more. The sooner you schedule, the more options you will have. Take-home problems. There's one from Module 4 and one from this module. They're due next Thursday by 5 p.m., regardless of when you're taking the exam. You can absolutely turn those in early, but that would be the absolute due time is 5 p.m. next Thursday. Okay? If questions about any of that stuff comes up, just let me know. All right, let's pick up where we left off on Thursday. We did an example of separation of variables. So here's what I want to do today. I want to do one or two examples of separation of variables from the worksheet, and then let you guys try some. Okay. And after that, we'll come back together. We'll look at applications. We'll do one off the worksheet, and then I'll let you guys try one off the worksheet. So today will be a little bit of back and forth because my main goal is to give you the opportunity to try some of these problems while you have people to ask questions. All right. So again, I've got the worksheet up. I'm on the separation of variables page, which is page 7. And I put that in the chat if you don't already have it open. And like I said, let's do 2 examples, and then I'll let you guys try some. Okay, so let's just go right with number 1. And now you've seen the online lesson. Last time you hadn't seen the lesson on separation of variables. It's actually a pretty cool little trick for these ordinary differential equations that we're looking at. All right, now all of them in here have an initial condition, so that's good. We get to practice with initial value problems. In this case, f of 1 equals 1. All right, so basically what's happening with separation of variables is we're separating the 2 variables to each side, and then we'll anti-differentiate both sides. And whatever is on top here on the left, that's what's going on the left. Whatever's on bottom here on the left goes to the right. So basically, I'm taking this piece and moving it over here via multiplication, taking this guy here, moving it here via division, okay? And we talked about this a little bit last time. You can only move things in separation of variables via division or multiplication. So basically, I multiply both sides by dx and divide both sides by y squared. I get dy over y squared equals x dx. That is separation of variables. Now, remember, you can only move things via multiplication and division, not addition and subtraction, and you need to move entire pieces. In other words, what I mean by that, if you look at number 3 here on the worksheet, that 3x squared plus 1, that all needs to stay together on whichever side it needs to go on. I think you'll get the hang of separation of variables really quick. But let's finish this one up and then see how we're doing. So once you've got them separated, the goal becomes to anti-differentiate both sides. So we need to do whatever we need to take these anti-derivatives. Now this is where we start to get back into stuff we've done previously, in case they're not basic anti-derivatives. These aren't too bad and these won't take too long. But what I mean by that is you might have to use U-Substitution or integration by parts, some of those techniques that we saw earlier in the semester. Now this one is basically just a power rule. Another thing to be careful of, because a lot of these end up being dy over y, we end up getting an antiderivative of ln of y. But this is dy over y squared. The antiderivative is not, I repeat, is not ln of y squared. This is a power rule, right? So this would be the same as y to the negative 2 dy and x dx. And now we take the antiderivative of both sides. We're basically back in Calc 1 mode at this point. So increase the power by 1, divide by the new power. So y to the negative 1 over negative 1 equals, this is an easy one, right? X squared over 2. And we do need a plus c. We don't need to do it like we talked about last time. We don't need to do it on both sides. So we typically just add it to the right side. Okay. Now, I'm going to show you a couple different ways of handling this, and you can decide what you guys like better. I talked a little bit about absorbing constants last time. So I want to show you what that looks like. But if I didn't want to go that route, I could put in my initial condition. In other words, x is 1 and when y is 1, I could put that in now and solve for c, or you can solve for c later. What I want to show you though is what I mean by absorbing a constant, and then you can always plug in the initial condition later. You plug it in whenever you feel is convenient. So I'm going to call this, instead of just calling it c, I'm going to call it c1. So it's basically the first constant. Well, I want to get rid of this negative, so I'm going to multiply both sides by a negative 1. So over here, that basically just gets rid of the negative. And instead of writing this as y to the negative 1, I'm going to write this 1 over y. Over here, what does that do? Well, I distribute that, and I get the negative x squared over 2. And typically, we would say, okay, minus c1. Well, what we do when we're absorbing constants is we keep this plus, and we call this maybe c2. And that's where c2 equals negative c1. That's called absorbing a constant, because I just want to keep it plus c at the end of the day. It's not going to matter once I plug in my initial condition. But I want to denote that I did change the constant because of distributing the negative. So this is what's called absorbing a constant. You see this a lot in differential equations, because a lot of times we solve for the general solution first and then absorb the constant later. All right. Now, we're going to need to solve for y. This will be easier to solve for y if I have the right-hand side as a single fraction. So let's come here to give ourselves a little bit more room. So here's where we are. Negative x squared over 2. And maybe I write this as, I'm going to absorb another constant, but I'm going to do it in 2 steps so you guys can see it. 2c2 over 2. So I got a common denominator. But I'm going to let 2c2 get absorbed into another constant, so I don't have to worry about the 2. Basically, what we're doing, we're trying to keep this thing as simple as possible. And you'll see why I want to combine these here in a second. What I have is negative x squared plus c over 2. Much more simplified than having to make it negative and doubling it and then having to undo that later, because at some point we're going to have to solve for c. And again, guys, you know, I chose to go this route because I wanted you to see absorbing the constant. We could have solved for c back at this step here. Okay. As always, guys, if you have questions about any of the steps, feel free to let me know. I can always pause and we can go in more in depth. Now, the reason I did this is because now I have a fraction equal to a fraction, which means their reciprocals are still excuse me, still equal. So I'm just going to flip both sides. So y equals 2 over negative x squared plus c. All right. Last thing we have to do is we do need to solve for c. This is where we'll plug in our initial condition. So y has to be 1 when x is 1. So we have negative 1 squared plus c. The 1 gets squared first and then made negative. I'm going to get this term out of the denominator. So negative 1 squared is just negative 1. Multiply both sides by negative 1 plus c and negative 1 plus c. Gets rid of that. So we end up with negative 1 plus c equals 2. And adding 1 to both sides, we're going to get c equals 3. And I'm going to have to skip over there. We've got our final solution. Y equals 2 over negative x squared plus 3, which is the unique solution to this initial value problem. We talked about that last time, the terminology, which is a differential equation with an initial condition that allows us to find the unique function that satisfies this situation. Questions about this one? Okay. Then, do you think you guys are ready to try one, or do you want to see another example? Let me know in chat which is it. Okay, let's try some then. What I'm going to do, right now we've only got 3 of you, so I'm just going to put you in one group so that you guys can talk to each other. I did number 1. We got 2, 3, 4, 5, 6, 7 to choose from. What I would like you guys to do is you guys can do whichever ones you want. If you want to do ones that look a particular way, go ahead. Choose any of these that you want to try. And I'd like you to do 2 of them. And once you've done 2, once you've done 1, let me know. I can always check the answer or if you have any questions. But let's do 2 of them. Any 2 you guys want, you guys can choose. We'll get through those 2, and then we'll come back together and talk about applications and how we set those up and solve them. You guys have the worksheet in chat, so let me put you guys in a room so that you guys can talk to each other. Call me in, guys, if you have any questions. Okay, you should have an invitation to the room. If you don't mind working on your solution on a whiteboard, that way if I do come in, I can actually, I'm able to see what you guys are working on, and you have something to post afterwards too. Okay. Again, choose any ones you want. Let's have you guys do 2 of them. I just want you to feel comfortable with separation of variables. So what we're going to do is we'll start number 2, and then I'm going to want to give you guys some time to try and work on it, because again, it's a really good differential equations problem, but it's not really obvious the first time you see it. So we're told that Newton's law of cooling says the temperature of a hot object or a cold object, it goes for both directions, decreases at a rate proportional to the difference between its temperature and that of its surroundings. So from there, That sentence allows me to set up my differential equation. So I'll use capital T for temperature and little t for time. So that'd be the rate of temperature in our differential equations notation. Is proportional. So that means it gets a constant of proportionality. I like using K, but guys, you can use any letter that you're not already using in the rest of it. The difference between the temperature of the objects, that's our variable, and the temperature of the surroundings, which in this case is the temperature of the room. So this is a differential equation because the rate the temperature changes is proportional to the amount. Now, in this case, it's the difference between the amount and the temperature of the room, but it's still this idea of it being proportional. Any questions about that initial setup? Okay, let's talk about how we would go about solving this one, and then I'm going to cut you guys loose to solve. Let's talk about what we know and what we don't. All right, so now when a person dies, the body, which is at 98.6 degrees Fahrenheit, cools to a temperature of 95 after 2 hours. That gives us 2 pieces of information. That means initially, so at 0 hours past, the temperature is 98.6 degrees. And then again, at 2 hours, it's 95. These combined are our initial condition. We also know that the temperature of the room is 68. So that 68 can be plugged in now. Equals K times T minus 68. And we're ready for separation of variables. Now, once we do our separation of variables, we're going to use both of these initial conditions. We're just going to take them one at a time. And we're going to use this one first because that 0 is going to be really powerful. So we use this one first, and then we're going to use this one. So this one here is going to get that multiplicative constant that we were talking about. This one here, once we have that, is going to help us find K. Now, what do I want? Here's what I want to check with you guys. Do you guys want to go into a breakout room and work on the rest of this one? Or do you want to continue to work on it as a class? What do you guys think? What would be more beneficial? Sorry, Taylor, I think I cut you off.
Oh, it's up to the other two. I did this in the lesson, so.
Okay, so you're already pretty comfortable with this one?
Yeah.
Oh, maybe that's a better question. Do you guys want to continue to work on this problem, or would you rather work on it differently?
I think maybe we should finish this one as a class and then work on another one.
All right, let's do it. Yeah, totally fine, guys. This is your time. I want to do what's most useful. Let's keep going through this one. This is an involved one. So let's go through this one. We'll see what kind of time we have left afterwards. So, all right, we've got our differential equation set up. Now it's time for separation of variables. I'm going to leave the K on this side, but I've got to move this whole thing because I can't just move the T. So that's what I was talking about in the last one, where you got to move the whole thing. So when I separate, let's change colors and make this. When I separate, I'm going to have dt over T minus 68 equals K little dt. So that's taking this guy, putting it here, taking this guy and putting it here. So that's our separation of variables. Questions about how I separate this. And as always, guys, if you want to pause me to ask a question, feel free. Integrate both sides. Here, this is actually not bad. It's just ln of, we can put an absolute value. We know it's going to go away here in a second. once we solve for t, but that's what we need so far, kt plus c. So you see it looks really similar to the one we just did. I've anti-differentiated both sides. We'll take care of the constant here in a second. Next thing we do is make both sides exponents of e. So what I end up with is t minus 68 equals, now I'm going to, just like we did before, I'm going to turn that into a multiplicative constant, a e to the kt. Okay, so I absorb e to the c into this new constant.
I was curious. So why is there only a plus c on one side and not on both sides?
It's because we're just going to absorb it into the one side, and what that means. Let's say we did it on both sides, right? I'll erase this. Actually, let's just go over to that. Let's just say we did it on both sides, right? So we have the ln of t minus 68 plus c1 equals kt plus c2. The very first thing we would do if we did this is bring this over to here, right? So we would have ln of t minus 68 equals, and what would that look like? kt plus c2 minus c1. But this, we would just absorb into another constant. So we would just say, okay, equals kt plus c. And, you know, like where c is just c2 minus c1. So basically what we're doing is omitting these first two steps by saying, hey, we know we're going to absorb it into another constant anyways. So let's just put a constant only on the right-hand side.
I see. It's because it's redundant.
Well, exactly. You got it. Okay. So everybody okay up to here? The t minus 68 equals a e to the kt?
I guess I'm just wondering where the a came from.
Sure. So right here, this is similar to the last one. Properties of exponents allow us to say, okay, well, that's e to the kt times e to the c. Well, c is a constant, e is a constant, so e to the c is a constant. So I'm just absorbing that into another constant and calling it a.
Okay, that makes sense.
And you know, it's one of those things, especially with ones like this where we have to solve for the variable by making both sides exponents of e. You're going to see this and do this so many times that it becomes second nature. Once you make both sides exponents of e, you just go to the multiplicative constant. You don't really write this part here out. Okay. Our goal is to solve for t. So I'm going to add 68 to both sides. You can put it before or after. It's really not going to make a difference. And we have two unknowns here, a and k. But we have two initial conditions. We're going to use this one first and then this one. The reason being is that t of 0 works very nicely in our favor. That's basically saying when little t is 0, the temperature is 98.6. So let's change colors for putting this in. So that tells us that 98.6 equals 68 plus a e to the k times 0. But k times 0 is 0, e to the 0 is 1. So really it's just saying 98.6 equals 68 plus a. And so that really quickly just gives us that a equals 30.6. So now here's where we are at after that blue step. We have 68 plus 30.6 e to the kt. We're fine with little t being in there. That's our variable. It's this k we have to find. But it's our only unknown now. So now we can insert initial condition number 2. But before I do, I just want to make sure everybody's okay with where we're at.
Yeah.
Okay, great. So now we're going to use this initial condition, which says t has to be 95 when k is 2. And again, this just comes back to solving this equation. So we're basically going to go through our normal steps of solving. Oh, sorry, go
I
ahead.
made that mistake too. T is 2, right?
Yep. Thank you.
I made that mistake too.
Yep, k is what we're trying to solve for. These two. Sorry, guys. I appreciate the help there. Now, guys, comes our normal solving step. Subtract 68 from both sides. 27 equals 30.6 e to the, if we want, we can write it as 2k. And here's the thing, I want k to be as accurate as possible. So I'm going to say, I'm going to leave it as an exact answer. Now, as long as you hold enough decimal points on this problem, it's really not going to make a big deal, a big issue. But I just want you to be aware that that's the way that I'm thinking about this one. So right here, 27 over 30.6. We're going to have to do something you might not have done in a while, which is solve for an exponent that's in a variable. So I'm going to take the natural log of both sides. I'm using natural log because of the e, because natural log of e is 1. And so that right-hand side just becomes 2k. All right, that's our property of logs. Natural log and e are basically inverses of each other. So to solve for k, I finish up by dividing by 2. Not a pretty number, but this is exact, and I can deal with that being exact. So we now have a model for this temperature problem. So let me go start out. All right, so here's where we are now. So now we have our model. T equals 68 plus 30.6 E, and this is going to be a little bit, not the prettiest of numbers, but 1/2, instead of dividing by 2, I'm just trying to clean it up a little bit. 1/2 natural log of, and we had 27 divided by 30.6, and there's our little t there. This is the unique solution to that differential equation. So now, if we want to find out how long this person has been dead, well, we know that when the body is found, it's found at 86 degrees. So now we know the temperature, and we're going to solve for little t. Now the solving steps are going to be exactly the same as the steps that we used to find k. So I'm not going to go through those again, but when you solve this, you're going to get that t is approximately 8.4789. And now we need to make sense of that number. What are the units on what do you think the units are on the 8.4789?
Hours.
Very nice. Here's the thing. we did the whole problem in hours. Our initial condition, the time was given in hours. What we found was a time, so it is automatically in hours. Now we can convert this to any time units we want. We've got about 8.5 hours there. And so we know that the person has been deceased for about 8.5 hours. Now, to answer question C, it says, what time or when was the murder committed? Well, it was about 8.5 hours before 4 p.m. So for us, that's around 7:30 a.m. Maybe we should say around because it's not exact. So that would be about the time that this person died. So, you know, we want to make sure that we completely answer the question, not just solve the differential equation. Like I said, this is a really cool problem because it's a very quick, very nice real world example of how differential equations get used because we have an amount proportional to a rate. Any questions about this one? Okay. Looking at the clock, I don't know if I want to have you guys start another one. Let's do this. You know, we've got about 20 minutes left. I want to open up the floor to any questions about differential equations. You know, there'll be more time for questions on Thursday about more general stuff, the final and other modules. But is there any questions that you guys have about differential equations, about the lessons that you've seen so far, the problems you've seen so far, anything we've done so far that you guys would like to look at? That would be helpful before we end today. So I'm just going to kind of throw it to you guys and see what you guys want to do in this last little bit.